All right, future architects, let's jump right in. Today, we're going to talk about something really forward-thinking. Forget just sustainable design for a second. We're going to explore a future where our buildings aren't just built, but are, well, they're alive. I'm talking about structures that can breathe, adapt, and respond to the world around them, almost like a living thing. And to really get why this is such a game changer, we first have to understand the massive problem it's trying to solve.
So, let's start with the big issue we're all facing. Take a look at this number, 60%. That's roughly how much of the energy used in a typical building goes directly to heating and cooling. Just think about that. It's a staggering figure, and it points to a really fundamental challenge in how we design our buildings.
So, here's our game plan for today. We'll kick things off by digging into that huge energy problem. Then we're going to explore this radical shift in thinking, from static buildings to adaptive ones. That's going to lead us right to the heart of our topic, the living bio-facade. We'll check out how it performs, how it's designed, and then we'll look ahead to the future of our cities.
Okay, let's get into our first section, the challenge of static design. Because that 60% problem, a huge part of it comes from a design philosophy that we've been using for, well, centuries.
I mean, think about it. Most building skins or envelopes are totally rigid. They're just static barriers. They're designed to do one job, whether it's a blazing hot summer day or a freezing cold winter night. They can't adjust to the sun, the temperature, or even what the people inside need. And that inflexibility is exactly why our heating and cooling systems have to work so hard, leading to that massive energy bill.
So if the problem is a static way of thinking, the solution has to be dynamic, right? It demands a total shift in how we think about a building's skin. And that brings us to Section 2, a new paradigm. And the key idea here is something called biomimicry. Now, this isn't just about making a building look like a leaf or a seashell. No, true biomimicry goes way deeper. It's about understanding and applying nature's underlying processes and systems. The brilliant strategies that have allowed life to flourish for billions of years. And when we apply that principle, we get the adaptive facade. Unlike that static barrier we just talked about, an adaptive facade can actually change its properties on the fly. It can respond to sunlight, to the weather, all with the goal of keeping people inside comfortable while using as little energy as possible. It's like a skin that thinks. Which brings us to the main event. What happens when you take biomimicry and adaptive design to their absolute extreme? Well, you get Section 3, the living bio-facade. A solution that is, you guessed it, literally alive.
Take a look at this. This isn't just some random, cool-looking pattern. It's a building substrate, and its complex geometry is directly inspired by the structure of coral colonies. That structure isn't just for show. It's a design perfected by nature to maximize surface area and manage resources. This is basically the skeleton of our living building skin.
So what brings this skeleton to life? Well, inside all those little nooks and crannies, we house photosynthetic microorganisms called cyanobacteria. These tiny little guys turn the entire facade into a biological system. When the sun hits the building, they do their thing. They perform photosynthesis. They're capturing CO2, releasing oxygen, and turning solar energy into biomass. The building is literally breathing. Okay, that all sounds incredible in theory, right? But how does it actually perform in the real world? Let's move on to Section 4 and really look at the evidence to see how this stacks up against what we're using today. This is the million-dollar question, isn't it? How does a living facade actually compare to other advanced systems, like a double-skin facade, which uses an air gap for insulation, or even a green facade that's covered in plants? Okay, let's zero in on two huge differences here. First, let's talk shading. A standard double-skin facade uses static things like louvers or plants. But the microalgae facade, it provides adaptive shading. As the sun gets more intense, the algae grow denser, which naturally provides more shade. It's brilliant. And second, look at the solar thermal function. The biofacade doesn't just block heat, it uses it to create biomass, which we can then harvest for biofuels. That is a total game changer. The building goes from being a passive structure to a productive one. So how in the world do you even start designing something so complex and organic? You can't just sketch it on a napkin. It takes a whole new way of thinking about design. And this brings us to Section 5, the process. It's a method called generative design, and it basically mimics natural evolution. You start by telling the computer your goals, like, say, maximize light but minimize heat. Then you let the algorithm go wild, generating thousands of different designs. An evolutionary solver acts just like natural selection, getting rid of the weaker designs and combining the stronger ones until the best possible solution emerges. The architect's job changes from just drawing one thing to, well, curating the best outcome from a whole ecosystem of ideas. And here's how that wild digital concept becomes a real thing. You can see the coral-inspired substrate attached to the building as an outer layer. That space in between creates a cavity, which turns the whole thing into a super high-performance double-skin facade. This is where the theory really hits the pavement, showing how this living skin can be integrated into our actual architectural language. So, what's next? Where's all of this headed? For our final section, let's look to the horizon and talk about both the incredible potential and the very real challenges that are still ahead. The benefits are, well, they're pretty profound. We're talking better comfort for the people inside, amazing energy performance, cleaner indoor air, and get this, it's actively pulling CO2 out of the city air and even generating fuel. The building actually becomes a net positive for its environment, not just to drain on resources. But we have to be realistic here. This tech is still new. There are some big hurdles to clear. For one, scaling this up for a giant skyscraper is tough. We also need more research on its long-term durability. And of course, these are living organisms. They need the right conditions, the right amount of light, the right temperature to really thrive. And that can be tricky to maintain on a building in different parts of the world. So this brings me to my final question, and it's a question for all of you. The very principles of architecture are shifting right now. We're moving from an industrial mindset to a biological one. So as you go out there and start to shape our world, you have to ask yourself this. Are you going to keep designing buildings that are simply built, or will you be the ones to start designing buildings that are grown?